Now, after the extraction of aluminium, we will see the extraction of the other metals. So, for the extraction of the metals, generally what we do is that these are the steps I've told you earlier. That we take the ore, we go for crushing and grinding of the ore. Then we go for the levitation of the ore. Then we go for the magnetic separation if it is required. If the ore is magnetic or if the impurities are magnetic, the gangue particles are magnetic, then we go for magnetic separation. If it is a sulfide ore, then we go for froth flotation or we go for leaching. So this is called as the concentration of the ore. The first is your concentration of the ore. Now after doing these things, we get the ore which is called as a concentrated ore. Got it? That is after crushing and grinding, levitation, if magnetic separation is required, if froth flotation is required, if leaching is required, then ultimately after concentration of the ore, the one which we get, that is called as a concentrated ore. Now the concentrated ore, what we'll do is that we will go for roasting or calcination. Got it? And then we'll go for reduction or smelting. The reduction can be chemical reduction or the electrolytic reduction depending upon the type of the metals which you are extracting. If you are extracting a very reactive metal like sodium, potassium and all those things, then we have to go for electrolytic reduction, that is called electrometallurgy. Otherwise we can go for the extraction of the less active metals, that is the chemical reduction, we can say that. So from the concentrated ore we get the raw metal, the crude metal, we can say that. The not the pure metal, the impure metal, we get it. Got it? From the ore we get the concentrated ore after concentration. Then after concentration we go for roasting, calcination, smelting or reduction, that is chemical reduction or electrolytic reduction. So where we get the crude metal, we extract the crude metal or the raw metal or the impure metal, whatever you can say. Now this crude metal or the impure metal, we go for purification. Definitely we'll remove the impurities. So we can go for either liquefaction or the poling or the cupellation, or electrolytic refining or zone refining or Van Arkel method, we can say that. There are different methods are there. So we go for and we get the pure metal, so to say. Clear? So these are the different steps. First the ore, then the concentrated ore after concentration, then we get the impure metal, the crude metal, then we go for purifying of the metal to get the pure metal. So purifying can be done by either liquefaction method or by poling method or by cupellation method or electrolyte refining method or the zone refining method or the Van Arkel method. Got it? In this way, any of the method we can go for and we can get the pure metal, so to say. Clear? So under that only we are coming for the extraction of iron. The picture we can see is the calcination process that is being shown here. Calcination is heating of the ore at a high temperatures in the absence of air or oxygen below its melting point. The main purpose of the calcination of the ores is to convert the carbonates and the hydroxide ores into its oxides. That means we convert it to its oxides during calcination. Alright, during calcination and roasting, what we do is that we convert the oxide, what you can say, the carbonate ores, the sulfide ores, the hydroxide ores into its oxides. Why? So that it can be easily reducible. It can be easily reduced because after the next step is nothing but is your reduction. So, for example, you can see here zinc carbonate on heating gives zinc oxide and carbon dioxide. It is being heated in absence of air, no oxygen is being used, we can say that. Calcium carbonate gives calcium oxide and carbon dioxide and heating. See, all is converted into its oxide. Aluminium hydroxide and heating will give you alumina or aluminium oxide and water. So all it's being converted into its oxide during calcination and roasting, depending upon whether we should go for calcination or roasting. If it is a sulfide ore, then we should go for what you can say roasting of the ore, and if it is a carbonate and the hydroxides ore, then we should go for the calcination of the ore, so to say. Clear? So after that we'll come to what you can say, it is nothing but known as a gravity method of separation. That is a gravity separation method, because that is a gravity separation method we use it. Rather you use this one earlier, before roasting or calcination, before calcination, we can say that it is being used, this particular method. You can use it after that also, but it is better to use before that. In the concentration step, it is better to use that you can see it here. A vibrating bed is being given here, vibrating bed, and the material is being impure metal, that is containing impurities, is being poured from the above, and a jet of water is being sprayed. By doing so, what happens is that whatever the gangue particles, the lighter particles, settles down and the heavier particles remains in the bed itself. The denser particles, the heavier particle, they remain in the bed itself, and the lighter particle flows with that of the water. But this method is seldom it is used. Why? Because sometimes if the ore is of lighter particles, if the density is less, then also it flows with the gangue particles, with the impurities. So hence we are not able to separate the gangue particles means the impurities from that of the ore. Generally we do not do it, but we use this particular one for the iron ore to remove the mud or the clay or the rags or the clothes or the twigs which is present in the ore. When we extract the ore from the earth surface, to remove this we use generally this particular method, that is your what you can say, the gravity separation method or levitation method, this is known as, or hydrolytic washing method, we can say that we use it. Got it? If at all the ores are bigger in size and the gangue particles are smaller in size, means there is a difference in size of the ore and the gangue particles, then also it can be removed by hand picking. Hand picking also is being done because the size and the shape of the particles, if it is differing, then the hand picking is being done. You can see your mother is being using this in the kitchen to pick the grams, the dals or the rices, or the rices I'm saying, sorry, or the rice from that of the unwanted particles, isn't it? Because the rice and the unwanted particles, they differ in size, in color, we can say that. So based upon that she is separating it, which is called as hand picking. Got it? She is doing it. So and she separates it. Got it? So in this way it is being done, this particular one. Sometimes we also go for magnetic separation method, also we go for magnetic separation, like for the hematite ore we go for the magnetic separation, where hematite is basically iron, what you can say, having strong affinity for uh, what you can say, that is nothing but known as that is magnet, and hence it is pulled towards the electromagnet, so to say. Alright, so hence we go for the magnetic separation, and the unwanted particles is being thrown away. Alright, that we are not using it, unwanted particles, so to say. Clear? So after, what you can say, concentration of the ore, after calcination and roasting, we will go for reduction. So where we generally do reduction, we generally do reduction in the blast furnace. The picture we can see there, it is nothing but the blast furnace. So the blast furnace, which you can see where the smelting is being carried out, where the reduction is being carried out, you can see the double cup and cone arrangement at the top, and we are having here three zones actually. That is a combustion zone, the reduction zone, the slag formation zone. Another zone also can be said, that is your zone of fusion, we can say that. The combustion zone is a lower zone where the blast of air and oxygen is being passed. Now you can see in the figure, that is your combustion zone, we can say that. That is a combustion zone which has got a very high temperature, that is 2170 Kelvin. All right, and you can see in the just below the combustion zone, you can see the molten slag, and below the molten slag the molten iron. Actually slag is lighter than iron and it floats over the molten iron, and also it is advantageous for us, as slag is lighter than iron, it floats over the iron. It is advantageous for us. Why? Because it prevents iron to get further oxidized. Alright, once the molten iron is being collected, it does not get oxidized further. Otherwise, again the same process. We are converting oxide, iron oxide to its nothing but to iron metal. And if at all it will get oxidized, then what is the use? So the molten slag, which is lighter than iron, generally slag is lighter than iron, it settles over the surface of the iron and prevents iron from being oxidized. So in the combustion zone, what happens is that carbon is being oxidized to carbon dioxide, and carbon dioxide is oxidized to, that is nothing but carbon monoxide. You can see that on the figure, on the screen you can see the equations, I am reading it out. That's a combustion zone where the temperature is 2170 Kelvin, very high temperature. Next comes is your reduction zone, that is your uppermost zone. The uppermost zone is the reduction zone, that is 1070 Kelvin, where the temperature you can see, that is your the reduction zone, we can say that, where iron oxide reacts with carbon monoxide, which is being formed in the combustion zone to form Fe3O4 and CO2. Fe2O3 reacts with CO to form Fe3O4 and CO2. Fe3O4 further reacts with CO to form FeO and CO2. Fe3O4 further reacts with CO to form FeO and CO2. FeO reacts with CO to form Fe plus CO2, we can say that. It forms Fe plus CO2. Now, this Fe and CO2 is being formed, we can say that. So, iron which is being formed in this zone is called as a sponge iron. it moves slowly down in the furnace, we can say that. Now the next is your slag formation zone. The slag formation zone is a central zone where the temperature is 1270 Kelvin, we can say that. The central zone, got it? That is your slag formation zone where the slag is being formed. You can see in the figure on the screen 1270 Kelvin, where calcium carbonate is broken down to form calcium oxide and carbon dioxide, which is the flux. Got it? Calcium carbonate, the limestone which I am adding it, that is your flux. That is being broken down to form calcium oxide and carbon dioxide. This calcium oxide reacts with silicon dioxide or manganese dioxide or phosphorus pentoxide to form what you can say calcium silicate, calcium manganate, calcium phosphate. It is going to form. Got it? Now silicates, phosphates and manganese are also reduced to silicon, phosphorus and manganese respectively upon heating with carbon. It is being reduced by carbon. Like SiO2 reacts with carbon to form Si and Co. P4O10 reacts with carbon to form P and Co. Again MnO2 reacts with carbon to form Mn and Co. These are partly absorbed by sponge iron, partly by the slag. Listen carefully. These are partly, this phosphorus, silicon, manganese, they are partly absorbed by the sponge iron, which is formed in the reduction zone, and partly by the slag. It is being absorbed. Okay. Got it? Now slag is your, what I said you, calcium silicate, calcium phosphate and calcium manganate. Got it? When calcium oxide reacts with silicon dioxide, silicon dioxide, manganese dioxide, phosphorus pentoxide, it forms calcium silicate, calcium manganate, calcium phosphate, which is known as your slag. And finally the zone which is 1570 Kelvin, that is the zone is known as the zone of fusion, just above the combustion zone, we can say that. So 2170 Kelvin is the combustion zone, I said you, the first zone. Then 1070 Kelvin, that zone we can see that is a reduction zone. 1270 Kelvin is your slag formation zone. And 1570 Kelvin on the diagram you can see that is nothing but known as a zone of fusion, we can say that. The zone just above the zone of combustion is a zone of fusion. In this zone the temperature varies in the range of 1475 to we can say that 1600 Kelvin, around, we can say that the temperature varies. Got it? The sponge iron coming down from the slag formation zone is being absorbed by, just now I said you, absorbed by carbon, silicon, phosphorus, manganese, etc. It melts in this zone at this particular temperature, that is 1570 Kelvin, around, we can say that. At the bottom of the hearth it is being collected. At the bottom of the hearth, HEARTH, it is being collected. Any iron oxide if left unreduced so far also get reduced by coke in this particular zone, and any impurities of silica or alumina still left combine with lime and form fusible slag. Got it? The slag being lighter floats over the molten iron, I've already said you, and it prevents the molten iron from getting oxidized. Now the iron which you are getting it, the first in the reduction zone, the iron which you got, that is a sponge iron, but the iron which you have collected here in the figure, which the iron which you are seeing, which is written molten iron, the purple color, that is called as a pig iron, which contains about 4% carbon in varying amounts of sulfur, silicon, phosphorus, manganese, etc. Got it? Which is called as a pig iron, which contains about 4% carbon and varying amount of sulfur, silicon, phosphorus, manganese, etc. We can say that. Got it? Now this pig iron is remelted in a vertical furnace heated by coke, and the molten metal is poured into molds, and the molds which you are getting it, got it, from the iron which you are getting it, that is called as a cast iron. So you can see how many changes it has formed. First reduction on the sponge iron, then you got the pig iron from the blast furnace, got it, and this is being collected in wooden vats in vertical furnace heated by coke, and it is being poured into molds, and the iron which you are getting it, that is called as the cast iron. Got it? Now wrought iron is almost the pure form of iron, contains impurities less than 0.5%. Is obtained from pig iron or cast iron by puddling process, we can say that. Clear? In this process, cast iron is mixed with some scrap iron heated on the hearth of a reverberatory furnace having a line of hematite, that is called as the puddling process. Alright, in which cast iron is mixed with some scrap iron and heated on the hearth of a reverberatory furnace having a line of hematite, we can say that. That is the wrought iron. But wrought iron, WROUGHT, wrought iron, it is of limited applications, the wrought iron, because it gets rusted very easily, so hence it is being converted into steel. We can convert into steel by the Bessemer process, by the open hearth process, and by the LD process. LD process is the most economical process because it involves less expenditure and is more productive. The operating cost is also low in LD process. LD has come from the word that is Lenz and Donawitz. These are the two scientists which is developed in Austria, not Australia, it is Austria, we can say that. And let me tell you, LD process is being used in route class steel plant. Got it? It is used in route class steel plant. LD process, we can say that. Where what you can say, the pig iron is being poured into a special type of converter, a pear shaped, we can say, converter, which is unperforated solid base lined with magnesite, and the pure oxygen is blown from the top. Got it? The pure oxygen is being blown from the top, we can say that. Clear? And the under 4 to 12 atmospheric pressure, and this blown oxygen oxidizes the impurities of silicon, manganese and carbon to the respective oxides which is being escaped into the air, and the slag form floats which is being formed floats on the surface of the molten metal, and it can be removed by tilting the converter. The slag is lighter, it is at the top, we can tilt the converter and we can pour the molten metal, and the pure iron which is heavier sinks at the bottom, we can say that. I was saying you the economical part of the LD process is that it involves less capital expenditure and is more productive. The operating cost is quite low, is also very low. It is quite fast and takes only just 45 minutes to treat one lot. In one lot means in one lot some tons of what you can say molten iron can be converted into steel just in 45 minutes, we can say that. And scrap iron can also be used in this particular process to convert into steel, we can say that. And the steel obtained is of better quality, is of good quality, we can say that. Clear? The steel, and the steel is of different types, you know, that's a mild steel, hard steel, alloy steel, stainless steel, nickel steel, manganese steel. Different type of steel is being produced by different heat treatment which is being given to the steel, that is your quenching, annealing, tempering, etc. we can say that. That's a different part, we can say. Now the one which you can see here is nothing but the froth flotation process, which is being used for the sulfide ores, we can say that. It is being used for the sulfide ores, the froth flotation process. It is generally used to remove the what you can say, the gangue particles which contains the earthly and the siliceous impurities from the sulfide ores of the some metals like copper, lead, zinc, etc. Got it? That is copper, lead, zinc, etc. They contain some earthly impurities, some siliceous impurities. So froth flotation process is being used to remove them. Now what we do is that we are taking the ore in the tank, we can see it, and we are passing high compressed air, hot compressed air, we are passing it through it. Got it? And the tank contains pine oil and a mixture of pine oil and water, and before passing the hot compressed air we are putting the ore. Now when you are passing the mixture of pine oil and water into this particular tank that is under high pressure, what it forms is that it forms froth. Got it? It forms froth. Now reagents such as aniline or cresol is added in order to stabilize the froth. Alright, aniline or cresol is added to stabilize the froth. They are known as froth stabilizers. Sodium ethyl xanthate is also being used sometimes, which is having the formula CH3CH2O CS2Na. CH3CH2O CS2Na, we can say that, which is known as sodium ethyl xanthate, is also being added. It is also known as collector, we can say that. Now the role of the activators is that certain sulfide ores have poor floating characteristics. Certain sulfide ores. Now it can be removed with the addition of certain activators such as which are themselves sulfides of some metals, like for example zinc sulfide has a poor floating nature. Got it? It does not form froth easily, we can say that. A special amount of copper sulfate is added during the froth flotation process. Copper ions combines with the sulfide ions to form copper sulfide, which gets deposited on the surface of ZnS, zinc sulfide. It has a better floating power as compared to ZnS, we can say that. Better floating power, it floats and it forms froth. It improves the floating characteristics of ZnS. It is very interesting to note here that the froth flotation process can also be applied to some non-sulfide ores with the help of activators. Got it? Like for example copper carbonate and copper hydroxide. All right. It's not as non. It is not a sulfide ore. It can be here. It can be added. Got it. It can be used. That is the here the what you can say. The activators which you're adding is your PbSO4. We are adding it, which forms copper sulfide and PbS on the surface of the ore particles, and as a result, they too can float. Now, when they float, a mixture of two sulfide ores as it is being formed. So what we are doing is that we are adding a depressant. We are adding, all right. For example, zinc sulfide and lead sulfide can be separated from each other in the Froth flotation process by addition of small amount of sodium cyanide, which acts as a depressant. Alright, as I said, two what you can say sulfide ores are formed. How will you separate these two sulfide ores? We will be adding depressant like sodium cyanide. It reacts with zinc sulfide to form a soluble complex. NaCN plus ZnS forms Na2ZnCN whole 4 plus Na2S. On the other hand, lead sulfide does not react with NaCN. It does not. It forms a froth with the pine oil in presence of air. Correct? That is what we do in froth flotation process. Generally, we add stabilizers, we add depressant, we add activators, got it, to form the froth. I hope you understood this particular one. That is a froth flotation process, generally which is used for the sulfide ores. Now after that, we will go for the roasting of the ore. We can say that. After this, what you can say, this calcination process, we'll go for the roasting of the ore. So during here it is being shown you that the copper ore I have shown you here. The concentrated ore is roasted on the hearth of the reverberatory furnace in a free supply of air, where the impurities like sulfur, arsenic and antimony, it forms oxide and it escapes into the atmosphere. Like S plus O2, it forms SO2. As plus O2, it forms As2O3. Sb plus O2 forms Sb2O3. It escapes in the air in the form of oxide, and the ore is converted into a mixture of cuprous sulfide and ferrous sulfide. You can see, alright, cuprous sulfide and ferrous sulfide. Now the sulfide thus forms get partially oxidized to the oxide, lower oxides, we can say that. Got it? The sulfide which forms gets partially oxidized into lower oxides. How? CuFeS2 plus O2 gives Cu2S plus Fes plus SO2. We can say that. Again, Cu2S reacts with oxygen to form Cu2O. Fes reacts with oxygen to form FeO. I said you, lower oxide. Now then what we will go for smelting. In the blast furnace, we'll go for smelting, where some of the sulfide ores which is not being converted into oxide is being converted into its lower oxide. During smelting, some of the sulfide ore which is not being converted into oxide is converted into oxide. During roasting, it is not being converted, but during smelting, some of the sulfide ores is being converted into its oxide. Alright, and also the ferrous oxide, it reacts with silicon dioxide to form slag, FeSiO3, it forms slag. And Cu2O reacts with Fes to form again Cu2S and FeO. This Cu2S is the molten mass which is taken out through a tapping hole, and it is called as MET. We can say that. You can see in the figure on the screen, you can see that is called as a MET, METTE. And it mainly contains cuprous sulfide mixed with some iron sulfide and unchanged iron oxide, we can say that. Now this MET, what we'll do, we will go for besmerization. For besmerization to get the copper, we can say that. During besmerization, what happens is that Cu2S reacts with oxygen to form Cu2O, and SO2 gas is released, and Fes reacts with oxygen to form FeO, and SO2 gas is released. Now when the SO2 gas is being released, alright, from the surface of copper, it forms blister copper, we can say that. It forms blister. It is known as blister copper because as the metal solidifies, the liberated sulfur dioxide gets produced. It looks like blisters on the surface of the metal, and this particular metal is about 98% pure, we can say that. Now this is the blast furnace which you can see it here, where the smelting process is being carried out. Just now I said you, got it? And after getting the 98% pure copper, we will go for the electrolytic what you can say reduction. Electrolytic refining. This is your electrolytic refining. You have read it earlier also, in which the impure copper acts as anode and the pure copper acts as cathode, and the impurities which is known as your anode murder slime settles down at the bottom of the tank, and the pure copper is being collected at the cathode. In this way, the entire process is being carried out and the pure copper is being collected, we can say that. That's all. Thank you.